All right. Hi, everyone. Welcome to lecture 11. We're going to start talking about continuity of functions now. So now basically our focus at this point is kind of shifting from sequences, which are in some sense more discrete objects. They're basically like functions on the natural numbers, right? We're going to shift to thinking about functions on the real line. So, things that you can actually draw with the graph that forms maybe some kind of a curve or something like that. And so the first thing we want to do is basically try to formalize the idea of when a function like this is continuous. Okay. So before anything really, I actually at this point, if you haven't watched the video I made about functions early on, I think it's just called A Note About Functions. I strongly recommend you watch that because the stuff in there is just going to become more and more important from here on. And if you don't understand some of the sort of foundations in that video, it's going to become extremely difficult to follow what's going on, especially because we're going to start talking about functions that have different domains. And like it's the definition of continuity is a little bit more subtle than you might realize, because for different domains, the continuous functions look different. Basically, like you can have functions on weird domains that don't look like they should be continuous, but they actually are. Okay, but so anyway, so definitely watch that. And in this video, I kind of just want to kind of talk informally about what we think continuity should be, what it should look like. And I think at the end, I'm probably going to end up stating what's called the epsilon-delta property of continuity, which will actually not be the definition that we use, but it's going to be equivalent to that. That's going to be the first thing we prove, is that the definition we actually take, which is the so-called sequential definition, is actually equivalent to the epsilon-delta definition. So yeah. So before we do that, I kind of want to like talk about, so what is a continuous, or rather, you know, when is a function continuous? When is a function continuous? Okay, and we'll be kind of trying to stick to, for this purposes of this, little discussion, I'll try to stick to examples that that feel more familiar and normal. Okay, so like for example, if this is a piece of f, if this is, yeah, I don't know, x, this is f of x, right? So here's the graph of f, and we would consider this continuous because, or at least just from looking at it, it looks continuous because if you look at the graph, it's not broken in any places, right? Another way, sometimes the way people describe this is that it's continuous if you can draw the graph in one motion without lifting. Obviously, these are dots for like showing that it continues, right? So that's not part of the graph, but you can draw the actual graph without lifting your pencil from the paper or something. So that's one way of thinking about it. So this would be continuous, right? It's continuous at all of the points here. There are no points of discontinuity, right? But a common way of, like, a common mental picture you might have for a discontinuous function would be something like where, let's say, it jumps, right? So, and this is often drawn like this, something like that, right? So here is a point of discontinuity, right? So if you just restricted your attention, so it's continuous over here, right? If you just restricted your attention, this is a common way for me to abbreviate this, by the way. Just restrict your attention to like a piece of the function over here, right? And ignore what's happening at this point. The function looks continuous over here, right? I can draw this curve right here without lifting my pencil. So it's really just this specific point that's a problem, right? So that's why, for one thing, you know, well, here, let me sort of, so this is discontinuous at a point. Okay. So the property of continuity rightly will be defined first in terms of like continuity at a single point. So fundamentally, continuity you should think of as being what we call a local condition, because continuity only depends on the behavior. Like continuity at a point only depends on the behavior of the function at like right near that point. Basically the behavior of the function arbitrarily close to that point determines whether it's continuous there at that one point. Okay, then of course we will make a definition of what it means for a function to be continuous, period, which is just saying that it's continuous at every point in its domain. But that is kind of an important thing. And what might be kind of counterintuitive about it is that actually it's possible for points that 2 points, no matter how close they are, cannot determine each other's, like whether the function is continuous at each other. Okay, so like if a function is continuous at one point, you don't know that it's continuous at any other points nearby necessarily. So you'll have to get used to that. That's part of the sense in which it's a local property. Another kind of a picture, oh yeah, and just to explain, so the circle here means that like right at this point the value of the function is defined to be up here instead of down here. I could have filled this one in and left this one open, and that would mean that the value of the function at this point is over here. Or I could have just put a dot down here and made both of these open, and then the value of the function would just be down here at this point. It doesn't really matter. So like another example would be something like this, where there's like a single point that's just randomly displaced, from this curve. So this is also discontinuous at this point, right? Okay, so these are some examples of discontinuity. I really want to warn you right away that not all discontinuities look like this. Okay, so these are like nice kinds of discontinuities. There are much nastier types of discontinuities that you can't even draw. Okay, these would be called jump discontinuities, and they are only one type of discontinuity. Okay, so just if you're ever trying to work with a discontinuous function, or sort of work with the hypothesis that a function is discontinuous, do not assume that it looks like one of these examples or even remotely similar to one of these examples. Just don't, okay? Don't do it, because it doesn't necessarily. Okay, so you'll come to see what that means more later, okay? Right, but so let's think about what we can take away from these examples, right? How can we sort of formalize the idea that the value does not jump around, or that we don't have to like lift our pencil from the paper as we're drawing the graph, right? How can we actually put that into, words and symbols in a way that we can work with it rigorously without any ambiguity about what it means, right? Well, one common way of thinking about this, and one kind of a quote unquote definition you might have seen before in like a calculus class or something, is that the function is continuous at a point if the limit of the value of the function as you approach, as x approaches that input value, if the limit of the output value equals the actual output value at the point, right? So in this case, that's not true. As you approach from this side, the output value approaches something over here, but the actual output value is up here somewhere, right? Or similarly, from either side, in this case, as you approach this point, this is called a removable discontinuity, by the way, because you can make this function continuous just by redefining the value at one point. So as you approach from either side, the limit of the output value is just whatever this value should be. But the actual output value at this point is up here instead, which is why it's discontinuous, right? So let's kind of write this idea down. So f is discontinuous at, or is continuous rather. F is continuous at a if the limit of f of x as x approaches a is f of a. Okay, so again, this is not the definition we're going to use. Okay, it absolutely is not a definition. So not the definition. Oops. Okay, at least for now, this cannot be taken to be a definition, partly just because these terms have no meaning right now, right? I mean, we haven't defined what it means to take the limit of a function of a real variable, right? The only types of limits that we even know about right now are limits of sequences, okay? So this is sort of an obstacle for us, but I just want to kind of examine how we might try to define the notion of continuity based on this idea, right? And the way we might try to do it is basically by looking at our definition for the limit of a sequence and seeing if we can kind of modify it in a way that makes sense to us for a function of a real variable, right? So like, how could we adapt the definition of convergence for sequences, basically, is what I'm saying. And if we remember, right, the definition of convergence for sequences, right, so basically it's like we're trying to say that f of x, in another way of wording this is like f of x converges, you know, quote unquote converges to f of a as x converges, well, maybe not converges, but as x approaches, meaning gets arbitrarily close to a. So as x approaches a, right? So we're kind of trying to impose this convergence condition. And you should think about like x here as being analogous to n, right? Because x is the input value. X is sort of like an index here. In the definition of convergence for sequences, x kind of, n is the index, and we're letting n sort of tend to infinity. Here it's like we're letting x tend to a, right? And then f of x is the output value, so that's like Sn, right? So in the definition of convergence for sequences, we had for all epsilon greater than 0, there exists an n, right, such that for all n greater than n, we have the absolute value of Sn minus S is less than epsilon. Okay, so if we make the analogy, right, that I'm talking about, where f of x is kind of analogous to Sn, right? X is kind of analogous to n, And then here, f of a is supposed to be the limiting value. So f of a should be analogous to s, right? So let's start to modify this stuff. And then capital N, right? Okay, so that's the most non-trivial thing to deal with. So let's ignore that for now. So we'll have for all epsilon greater than 0, there exists something such that for all x something, right? We have f of x minus f of a is less than epsilon. Okay, so that's starting to look a bit better now, right? Now here's the thing. So when we think about capital N, the role that capital N plays in the definition of convergence for sequences, right? What role does capital N play? Capital N is something that's supposed to sort of force little n to be large, right? Or rather, another way of thinking about it is it forces little n to be close to infinity, right? The thing is, in the context of sequences, whenever we think of the limiting process happening, we're thinking of n as approaching infinity, right? So that's kind of like the sort of infinite, like that's the limiting behavior of n itself, is approaching infinity. So n, capital N, forces n to be close to infinity, okay? So it's sort of like this like tolerance or a threshold on the sort of the input variable that forces the actual limiting process to be sort of going forwards, right? Now in this case, what we wanted instead of x like approaching infinity, right, is that we want the limiting process to happen as x gets close to a, right? So whatever this thing is here should be something. So this should force x to be close to a, right? So this number should sort of be like a tolerance on how far away. Capital N is kind of like a limit on how far away little n can be from infinity, right? This quantity should be sort of a limit on like a cap, right? On a boundary that determines how far away x is allowed to be from a, right? So this is for all x that are actually closer to infinity than n. So this is all n closer to infinity than capital N, right? This should be all x within, you know, something from a, right? So what we do is we give this variable here, this just has to be a variable, so it doesn't matter what we call it, but typically we call this delta, okay? So this is a delta, lowercase delta, and now this is for all x with x minus a less than delta, okay? So delta is sort of our, you know, is sort of the parameter that controls the limiting process, I guess is what I'll say. It's the parameter that controls how far away from a x is allowed to be. And capital N is the parameter up here that controls how far away from infinity little n is supposed to be, right? So this actually turns out to be, here, let me actually use a different color. So let's say, so this is actually almost a valid definition of continuity. I say almost just because there's actually an issue of this for all x. When we make the real definition, well, this won't actually even be the definition anyway, because we're going to define it in terms of sequences instead. But if you wanted to use this as a definition, you should really say for all x in the domain of f, for which this is true. Okay, and that introduces all sorts of weird possibilities. So I'm not going to really talk about it for now. But if you assumed, for example, that f was a function that was defined for all values of x in the entire real line, then this would actually be a valid definition. Okay, so now the reason we don't use this as the definition is actually more, I think, one of convenience, just because it's more convenient to make the definition differently, and then we can prove a lot of theorems kind of differently. But this is equivalent. This will be, at least the corrected version of this with the domain thing, will be equivalent to the definition that we make, which I'll do in the next video. So anyway, I kind of, oh, before we do that though, let me just draw a picture of how this looks. So I'm gonna make a little cut while I draw the picture. All right, so as you can see, I've sort of tried to draw a diagram representing the definition of convergence for, so this is like the n axis, and then this is like the Sn axis here. This is like the x-axis, and then this is like the f of x axis, right? So I tried to draw the definition of convergence for sequences, and then I tried to draw the definition of convergence for functions, at least functions whose domains look reasonable, okay? And so, yeah, as you can see, like here, right, the idea is that we can make this band around the limiting value s, and then we can use n to control little n and force little n to be so big that all of the values of the functions stay within the band basically from this point on. So, or all the values of the sequence, sorry. So the sequence is like entirely inside this rectangle that extends out. You know, the graph stays inside this rectangle that extends out from capital N to infinity, okay? For a function, instead of using, so this is like a plus delta, sorry, and then this is a minus delta. Instead of using some cutoff that forces x to be large, I guess, what you're doing is you're using a sort of a radius to force x to be close to a, which forces in turn, at least if the function is continuous, what we're saying is that forcing x to be close to a forces the function to be close to f of a. So the graph stays inside this rectangle, basically, where the height is, you know, I guess 2 epsilon. The vertical sort of radius here is epsilon, and the horizontal one is delta. And as you can see, it kind of gets close to, you know, exiting the rectangle right over here, but it's still okay. So the graph just stays inside this rectangle. If we accidentally chose delta to be, you know, a bit bigger, then there would be a piece of the graph which would be outside, you know, then our rectangle would just get sort of wider, basically, right? And then a piece of the graph would be outside, which is bad. And of course, we could choose delta to be smaller, right? Don't forget that, like, you can, for one thing, you can always choose capital N to be much larger than it has to be, right? Here, this is basically close to the smallest value it could be, but it could be a lot bigger, and that wouldn't be a problem. Same thing with delta. You can choose delta to be much, much smaller than it actually has to be, and that'll be a valid, you know, if you do that in a proof, it would be a valid proof. It would be a valid argument, right? So anyway, and as you can see, if we go back to, you know, these graphs, for example, in this one, how would we use the definition to show that this is discontinuous? Well, all you have to do is sort of take, take f of a, right? This is f of a, and then just draw a fairly narrow, you know, rectangle around it, and you'll get something that does not have, right? So here, it's like, no matter how thin we make the vertical rectangle, the graph, no matter how thin we make the vertical rectangle, for this value of the epsilon, of epsilon, there's no way to force the graph of this function to stay inside of this, you know, in some rectangle, you know, some vertical rectangle around, around x here, right? No matter how thin the green rectangle gets, there's going to be pieces of the graph down here right next to this point, which are outside of the actual, you know, the place where these two rectangles overlap, basically. So that's why this would be considered discontinuous. So anyway, this has kind of all been an informal motivational section. In the next one, I'll actually make the definition proper, and then we'll show that this quote unquote epsilon delta property actually holds. And then after that, we'll do some basic stuff about showing that, you know, you can do stuff with continuous functions, like add them and multiply them and so on. And actually, a nice thing about that is because we're using the definition with sequences, all of those things kind of come for free because we already proved the corresponding theorems for sequences. So you'll see. But that's it for this video. See you in the next one.